Hello everyone. Uh, Welcome to my presentation PI controller auto-tuning using fuzzy control and genetic algorithm. Um, so in this project, I will first introduce the paper that I referenced listed here. Um, and then we'll start talking about things that I disagree with this paper and my implementation. Then I will talk about the challenge encountered, then talk about the existing issue and a new proposal. Uh, then I will show some simulation results of my new proposal and then give a summary. This is kind of the overall implementation diagram of what is introduced in the paper. So basically, the genetic algorithm is driven the whole thing. In the first step, we need to encode, the information. In this case, non-parameters into the each chromosome, and the paper proposed initialize 20 chromosome. Each of these chromosome, if you decode that, it's gonna give you those parameters, and this parameter needs to be transferred into fuzzy control related parameters, such as the center of each membership function, like this W1 is the first center of this negative big function, and then this sigma 1 is the kind of the sprite. And then after you transfer the decoded chromosome into the corresponding control related parameters, you can start kind of evaluate this 5 root 5 input membership function based fuzzy logic controller, and it is using a CA defuzzification, and for each it is monitoring the input is the so-called tracking error, and this tracking error you will use that to evaluate the weights from each rule, and then kind of this is a normalized rule, normalized weight, and then this is the equation that finally figure out the currents. And in this paper, original paper, it does not give you the effective Kp and Ki. It only provides the currents. And later on, I will show that there is an equivalent form that gives you the effective Kp and Ki. And that one is actually the one that I desired, because in most company they are using PI controller, and they want to know exactly how much Kp and Ki you actually tuned for controller instead of just black box currents. So after this decoding one chromosome and then convert to those parameters, after evaluate the parameters, you can design certain commands here and certain load profile here, and then for that fuzzy controller, it's gonna run the simulation and gives you a response, and that response you can collect them, this tracking error and this currents, and you can evaluate the cost function. And for each chromosome, you will get one cost. And then I didn't show here, but for the GA implementation, we need to convert the cost function into corresponding fitness function using Goldberg transformation, and that basically is kind of embedded in this GA operation, and I didn't really show that in this overall diagram. And then the step 5 here, after evaluated the cost, we start doing the GA. We check for stop condition, and then if it's stopped, for example, exceed your maximum generation numbers, then we start, we keep track of what's the best chromosome at generation K, and what's the best overall chromosome appeared, meaning the lowest cost or highest fitness. And then if it's not stopping, then we kind of doing the J operation, like the selection by roulette wheel, and we perform crossover mutation and kind of generate the next generation. And this is some tuning notes. Basically, current regulator is sort of not the main focus of this project, but this is how it is tuned. It's based on the zero pole cancellation, and you based on machine parameters, you set to 100 Hz bandwidth. So this is a 100 Hz current regulator. This is a simple diagram showing you the plant model and the PI controller. And then the paper also proposed a tuning solution to kind of tune this KPKI if you know plant parameters. In this case, if you do the math, you will derive the closed loop transfer function, and it has this second order characteristic equation. And if we kind of set the damping and the natural frequency, and we set the natural frequency to be 10 times smaller than current regulation bandwidth, you can have a pretty good KPKI tuning. But this is assuming that you know parameter well. And these are things that I disagree with the paper. The paper basically suggested that we use this kind of method to have an initial tuning, and then that initial KP bar, KI bar, we can set to this rule 1 output and rule 5 KP to be same as that largest one, and then we can have that alpha 1, which is a parameter between 0 and 1, and then we can sort of times that and assign to K2P and K4P, and then this we times again another parameter that is between 0 and 1, and this will guarantee that we use that KP from previous derivation. We have this KP bar, and we use it as largest KP, and then this 1, 2, 3, 4, 5 is corresponds to 5 basically 5 membership function, which later on shows it's a negative big, negative medium, and 0 positive medium and positive big. So it's 1, 2, 3, 4, 5, and this will guarantee that we use largest KP gain when the omega e, when the tracking error is large, and then when the tracking error is kind of medium, we use a little bit smaller gain. When tracking error is 0, we use smallest gain. So similarly for Ki, this is proposed from the paper. And then this if you look at this fuzzy logic controller, if you kind of distribute this formula a little bit, you will see that this can be converted to the standard KPKI controller, but the KPKI is kind of scheduled by based on the tracking error. So I call this effective KP and effective Ki, because this part is timing the tracking error, and this part is timing the product of tracking, actually the integration of the tracking error. So with this proposed tuning strategy, you can never actually achieve better performance than if you just use this fixed gain, the largest gain, in terms of disturbance rejection, that's just my own opinion, because the paper actually showed the very superb disturbance rejection results. Basically, from this plot, you can see that this one is the proposed GA tuned result, and this one is the conventional, using that fixed KPKI, and then he is doing a step load from 5 Newton meters to 10 Newton meters back to 5 Newton meters here. You can see that he shows that the GA tuned one almost rejected the disturbance perfectly. There's no deviation on the speed response, and here there is a dip, and then when he removes the load, there is a surge on the speed. I personally think it's not possible, because if you use the GA, all it does is kind of at some smaller tracking error, it try to reduce the gain, right? But if you reduce the gain compared with you always use the largest gain, it's impossible that here you have no deviation, but here you actually have larger deviation when you use always fixed larger gain. So that just seems impossible to me. That's one thing that I disagree with the paper. The other thing is the paper suggested this GA setting, which maximum generation number is 50 and population size 20 and crossover rate 0.5 and mutation rate 0.5. I personally think this is not good way to utilize genetic algorithm, because the mutation rate is too high, which makes the group evolving too fluctuated, and it behaves almost like a random search. And I think a good set of gain can be like shown. And then in terms of the plant model, the paper gave you a simple plant model, simple dynamics to simulate, and it also tells you which solver to use. This solver is actually MATLAB ODE45, and it's a variable step Runke-Harder force solver. And just one thing to be clear, this omega t here is the electrical speed in R80 per second, but not mechanical. If you want mechanical, you need to convert that. And in the simulation, I listed here that if you want to ignore the current regulator dynamics, you can use this. But actually, in my simulation, I used a 100 Hz low pass filter to represent the current dynamics for my simple simulation. I have a high fidelity simulation later on. I will show you. It has all the dynamics, all the full current regulator, the PWM, and also the power stage. And then the fuzzification, basically we are monitoring this tracking error, and we are saying it has 5 kind of fuzzified linguistic variables, negative big value, linguistic value, negative big, negative medium 0, positive medium, positive big, and for the output, it's almost like the singleton output, crisp output. So this thing is similar to a TSK model, fuzzy model. And when it's PB, it is using some larger KP, and when it's NB, it's same as when it's PB, and then when this is PM, it is somewhere here, smaller than that, but larger than the 0 case. Similar case for the KI, and then just to just to point out, we are using the simplified product inference engine for the inference. And then the rule base, just based on my implementation, I have to convert the single input two output system into kind of a single input, single output version. This is just how I implemented it. And equivalently, I have to convert that 5 rule into 10 rules, such that if this omega e is NB, Kp is equals to K1, and the rule 6 is saying if the omega e is NB, Ki is Ki1. So you could say that if omega e is NB, Kp is K1p, and Ki is K1i. But in my implementation, I need to separate them. For the defalsification, like what I showed you before, I personally want the effective Kp and Ki to be represented explicitly instead of just give me IQ as command current. So in this case, this K1p, K1i, in the context of center average defalsification, they are the center of the output membership function. So the challenge that I encountered when I implement this first is when I apply the Goldenberg transformation to my cost. You see the worst cost here is very, very large, and the Goldenberg transformation basically flipped that cost and then shift it to make sure that fitness is non-negative, is positive. So I end up shifting the thing with 1.5786 to the power of 23. That shifting is too large, and when the number gets too large, the single precision can actually has very bad resolution, and I cannot differentiate even my highest fitness or the best objectives. So all these best objectives is different, but when you shift it into the maximum fitness, they can becomes similar number, just because this numerical stuff difficulty. And then my proposed solution is to modify the cost function to give it a hard upper bound as 1,000, because I observed that the mean cost is actually maybe 220 or something, or so I decided that this 1,000 is large enough, so I will cap it at 1,000. And when I do that, this is the first set of results that I got. When I set, this is the setting of the genetic algorithm, and I can see they sort of converge, but the maximum fitness is almost capped. And then when I saw this membership function, this positive medium and positive big, actually positive big and negative big, the spread becomes very, very big, and these ones are kind of tiny, which is not very good. I talked with professor that although we are tuning, these are all free to tune, but we have to add constraints such that it reserves a correct concept. This different membership function needs to be separated enough. And then I tried something like the paper suggested to give a very large mutation rate, 0.5, and the result is kind of similar, although I end up having a lot of fluctuation there, and so I really at this point I really think this paper doesn't make any sense. Just like what I mentioned before, you can never get a larger, better disturbance rejection performance when you use a smaller gain than what you used initially. And there's another challenge encountered is the paper used Gaussian, membership to create all the membership functions, and there it's not this negative big and positive big are not open-ended functions. So when you evaluate the weights at a certain point, it could becomes numerically, difficult to compute because these numbers get so small. And my I think this is just another wrong. And then I think this is the existing issue observed. The referenced paper did not give a good rule to constrain the center and spread of each membership function such that it could move too much and violate the original purpose of imposing the fuzzy logic control. For example, these centers of NM and PM, it could sort of overlap that of the zero, and then those NB and PB spread becomes super large. The universe another thing is the universe of discourse is not tunable, such that the maximum KP KI are not tunable based on the existing strategy. So the universe of discourse, this omega e 50 to negative 50, once you specify that, it's not tunable based on existing strategy. And that KP bar and KI bar, if you recall, we initially assigned as largest KP and KI bar. They are not tunable once assigned as well. So this triggered my thought also on presented results in the referenced paper. How could you achieve better disturbance rejection if all you are doing is to use some smaller gain, at some smaller tracking error region? That doesn't make sense to me. And then I have a new proposal. Basically, I try to make the universe of discourse by adjusting the user provided omega e max by a factor between 0.5 and 1.5. It's shown basically here. I let user define omega e max, or I can use a default value, for example, 100. Then this factor between 0.5 and 1.5, it can actually set my omega 5 at a value between 50 and 150 if this value is 100. So it makes this omega 5, this boundary tunable. And then I also add more constraints on how much each membership function could move to make the concept always conceptually valid. So what I did is I basically saying that once I figure out this omega 5, the omega 4 is actually equals to omega 3, which is omega 3 is always fixed at 0. It is equals to omega 3 plus a number times the difference between omega 5 and omega 3. So I could place the omega 4 in between omega 3 and omega 5. When it is 0.5, it's kind of point, omega 4 is put at the middle between omega 3 and omega 5, and when it's larger than 0.5, it's actually closer to the center of PM is closer to center of PB. So in this case, if it's closer to W5, I basically figure out the spread of this. Actually, even before I talk about this, I also changed the format of the membership function. If you see the membership function that was used in the paper, it's actually this format, and I changed that to this one. The reason is that in this format, this sigma does not really has a lot of physical meaning. But in this format, the sigma is actually point to this 0.61 location, and this is 1, and this is 0.61, and this is the sigma. So I determine the sigma 4 to be equals to a factor times this omega 5 minus omega 4, and then if this center W4 is closer to ZO to 0, then I basically use the distance between W4 and W3 and times a factor to determine my sigma 4. And once the sigma 4 is determined, I basically use this equation here to determine the my sigma 5. And the thought behind it is if this factor is 0, what I try to achieve is the sigma 5 plus 2 times the sigma 4 is equals to the distance. So if this is 1, what I try to achieve is sigma 5 plus sigma 4 is equals to the distance between omega 5 and omega 4. In that case, it just guarantees that basically the omega 5 is not too large or too small. In this case, it roughly shows you that sigma 4 and plus sigma 5 is equals to the omega 5 minus omega 4. So it's when this eta I2 is equals to 1. When it is equals to 0, this PB could move to the farther to the right, but that's the largest it can farthest it can go is to when the sigma 5 plus 2 times sigma 4 is equals to the distance here. So it's just more constraints, and similarly I have this sigma 3 defined as by this equation. Similar logic, when this factor is 0, I try to achieve 2 times of sigma 3 plus the sigma 4 is equals to the distance between W4 and W3. And when this factor is equals to 1, basically the sigma 3 plus sigma 4 is equals to the distance. It's pretty much what is shown by this graph. And then the center of the NB, the center of the negative big is just negative of the center of the PB, so it's kind of symmetrical. Similarly, the NM is symmetrical to PM, and spread wise, this sigma 1 is equals to sigma 5, sigma 2 is equal to sigma 4. And then this new proposal also, the fuzzy variable is not exactly normalized, but kind of close by after adding those constraints. that it does not exactly sum to 1, but it's kind of better than before, and it's close by imposing those constraints. And instead of using the sigmoid to achieve an open-ended membership function for PB and NB, I kind of clipped the Gaussian evaluation at the boundary of the universe of this course. So I know that where is this W5, and when it's outside, I just keep using the last value here. That's why in this diagram I put those mosaic there. And in this, it naturally kind of behaves like an open-ended membership function. You could also use like a sigmoid function, but then it makes this whole thing a little bit more complicated because sigmoid has two different parameters specify the shape. I just want to reuse as much as possible, so that's why I did this. And then this is a comparison between the original paper and my new proposal. The original paper, it has 9 parameters each chromosome, and then the once Kp bar and Ki bar is specified, it's not tunable, and then also there's no further constraints on this membership spread and center. It's free to move. The only thing it did was kind of 4 is symmetrical to 2 and 5 is symmetrical to 1. And in this case, I added more constraints, and I used a version, membership function that make more sense in terms of spread. And then in my implementation, I have 11 parameter per chromosome. And in this case, I intentionally, just to verify if the thing works, I intentionally created a set of gain that is unstable. So recall that if I set this damping ratio to be nearly 0, and then my current regulator bandwidth is kind of here, low pass filter is 100 Hertz. If I use this kind of setting, then I can generate a set of gain that is unstable. It is so this whole controller just does not work, and then I start from an unstable point to tune my controller, and then I observed that just after 5 generation, it minimized the cost quite well. This is the cost, and this one is the fitness. And then if you observe the fuzzy controller tuned system, the speed response is stable, and this is a zoom in plot, and then the original one is kind of all over the place, is unstable. And then this is the final result of my input membership function, and then this is the output for Kp and the output 2 for Ki, and then this is the effective input-output relationship, which is basically a lookup table for Kp and a lookup table for Ki. And I deployed those gains, basically these 2 tables found out by genetic algorithm and fuzzy logic. I deployed that onto my high fidelity simulation here, which includes the whole current regulator and the PWM, and also the I was not able to capture that, but also the power stage. In this case, the simulation results is quite similar to what I got from my previous analysis using simple dynamics, and there's more current ripple here it's understandable there's PWM switching. And so this kind of gives me confidence that this fuzzy controller has high chance to work for a real system as well. Although for a real system, we have to add more logic to basically saying that if the cost goes out of bounds, if the cost goes higher, we want to skip this profile and then give it a high cost. Basically, we want to avoid this type of unstable thing to damage our system. In simulation, you can have this, but in a real system, we want to avoid this. So there is some more logic we need to add, kind of like a protection. But this shows me it will work. This is an updated overall implementation diagram. I basically replaced this with 11 parameters, and this is the decoding strategy to transfer the GA parameters into the control-related parameters. And then this fuzzy controller also, instead of having a IQS, I have an effective KP and KI, which finally gives me IQS, but I want them to be represented explicitly, such that I can explain to other control engineer or audience what exactly what KP and KI is commanded. This is the summary. So in this project, I built a tool that can auto-tune the SPM motor speed control without even knowing any plant model information. So it can provide a controller even starting with some initial unstable gains. So you can see this input MFs is free to tune, and the universe of discourse is also free to tune. Because here you can see that it's roughly 90, and here is roughly 120 or 150. And then this output, KP1, KP2, KP3, KP5 are also free to tune. And of course, the final effect is every fuzzy logic controller will embody itself into basically two lookup tables, one for KP and one for KI. They are lookup table in terms of the tracking error. And just as a demo, that's here you kind of set some the GA related parameters. Let's just use 0.9 crossover and 0.1 mutation, and then if you run this, it will start kind of, this is the membership function, and then it will start tuning those membership function, and each of these fuzzy logic controller embodies itself into kind of this type of lookup table, and then the gain of the lookup table, the largest gain here is free to tune, and also the universe of discourse is also changing. If you notice, right now it's around 70 maybe, and then it changed to maybe 150 or something, and then during the process we have certain command and disturbance profile designed, and then this is collecting the system response in terms of speed response and current command. And then after each basically population size is 20. After each generation, it's gonna show you some cost results. We can see some of the controller tuning gains kind of have a better response already. And look, like what I said, we will not allow this type of response to appear in the real system. So there's more things to do to write some state machine or whatever. When we observe unstable behavior, we should terminate that specific wrong and then just label it as a highest cost. So we can see this generation one. This green dot shows you the mean cost, and this red one is the average cost in this generation. And after another 20 population size is 20. After another 20 runs, there will be another point in for generation two. Since it takes some time, I will stop here. This is just illustrate how it works, and the final result I already presented in my presentation. Basically, it after five, even two generations, it already achieves some very good response. Thank you very much.